Okay, so today we'll see lower bounds for universal relation. So let me start by reminding you what universal relation was. This was a weakening of the KW relation associated with a function. So given a universal relation, given an input size, let's say m, the relation is the following game. Alice gets a string x, Bob gets a string y, both are n-bit strings, and their goal is to find an index I in n such that xi is not equal to yi. And this is a promise problem, as I was telling you in the earlier lectures. So the promise is that they need to run the protocol correctly on inputs where x is different to be guaranteed to be different from y. So promise is that x is not equal to y. So what we want to prove is that this is indeed a hard problem. So a trivial protocol for solving universal relation would be where Alice sends x and then Bob can figure out which index he differs in and send that index back to Alice, and this would cost something like m plus log n bits, and we'll see a lower bound that this is sort of needed. So our goal today is to prove a lower bound for which says that communication complexity of universal relation on m bits is at least m minus 2. So maybe I need to make it m minus 3, but m minus some constant. So this is like very hard. So before proving this lower bound, I want to tell you some philosophy behind why this problem should be hard. Why should we expect to prove such a lower bound? Okay. So one easy way to prove something weaker is to realize that we saw this thing that for the universal relation is a generalization of the Kashmir-Wheaton relation associated with any function f. So in fact, for any Boolean function f on m bits, if you have a protocol for universal relation of cos c, then you can run the same protocol to solve the Kashmir-Wheaton relation associated with f. So we know that the communication complexity of the Kashmir-Wheaton relation of f is at most the communication complexity of the universal relation, because in the Kashmir-Wheaton relation all these promises are kept. So Alice and Bob can run the protocol and find an index. And we also know this fact that the Rex's functions were depth of f is at least something like m minus log m. So we know that by the Kashmir-Wheaton connection, the depth of f is equal to the communication complexity of KW of f. So by plugging in this hard function, we get a really good lower bound already. So this is for all f, so it should work for this particular f also. So by plugging in that, we get that the communication complexity of the universal relation is quite high. But this is a very specific kind of lower bound, and it has this minus log m factor, and we want to do something like m minus a constant. And to do that, we'll introduce some philosophy on why this is hard, and this philosophy is going to be the guiding principle behind attacking the general conjecture as well. And we'll use this philosophy to also build on proving lower bounds for compositions of universal relations. So remember that end of the day, we want to get to compositions of functions or universal relations, and we want to do we want to come up with some kind of general philosophy that tells us that why KRW conjecture might be true. Okay, so enough about that. So what is this philosophy? To understand this, let us reconsider. So what does universal relation look like? I claim that it looks somewhat like equality. Although the only problem is that, so if you remember, the equality problem versus function equality that the players have to compute. Alice is given x and Bob is given y, and they want to know if x is equal to y bit by bit. And we sort of saw proof that equality is hard. So to compute m bits equality, you need something like m minus some constant bits of communication. You actually can prove that you need m bits of communication. And I want to claim that this equality problem is hard because there's some kind of inherent symmetry in the inputs that players can get. So let's recap this equality function. So Alice is given x, and Bob is given y, and you want to find out whether goal, figure out whether x is equal to y. Okay, but you might think that okay, universal relation is like quite different from this, right? Universal relation, you have to figure out, you don't have to figure out whether the strings x and y are different. So you're already given the promise that x and y are different. You just have to find out an index where they differ. But I claim that that's only like a technical difference, and in fact, a generalization where this promise won't be true would be almost as hard as solving the promise version. So this is going to be a general theme later on in the course as well. So let's now define the non-promise version of universal relation. So I want to say it like I want to bring universal relation close to this equality problem. So I want to get rid of the promise and come up with a new relation. So this is the non-promise universal version of universal relation of universal relation. Okay. So this is quite simple. It's a simple generalization. Alice and Bob get strings x and y, and the goal again. So there, like earlier, there was a promise that x is not equal to y. So if x is equal to y, this so the earlier goal was that you have to find an index I in m such that xi is not equal to yi. But if x and y are the same string, there's no way they can find an index, right? And we are going to remove the promise that x is different from y. So our goal is going to be slightly different. So they have to find an index xi not equal to yi if x is different from y, and they can output perp if x is equal to y. So this is the relation. So they are allowed to output perp if and only if x is equal to y as a string. Otherwise, they have to output an index I in m where xi is different from yi. So it's not okay for them to like just start the protocol and say perp all the time, right? I mean, if I didn't have this condition, then they could just like without looking at x and y, they can just output perp. So they are allowed to. So the perp is like they're rejecting the input. So they're allowed to reject the input and say that we give up only if x is equal to y, only if they know that x is equal to y. So now I claim that okay, the communication complexity of this non-promise version is quite close to the promise version. So how do we do that? So let me introduce some notation for this. So we denoted the universal relation by un. So maybe this is like un dash um dash. So this is the non-promise. Okay. So I want to say that like we can prove a lower bound on the universal relation by proving a lower bound on the non-promise version. So the claim is that communication complexity of the universal relation is upper bounded by the communication complexity of the non-promise version of the universal relation plus log n. So if this is m, this should be m. Okay. Yes. So how do we do that? So what are we going to do? Oh, I'm sorry. The other way around. So this should be the communication complexity of the non-promise version of the universal relation. So this is the non-promise. It's upper bounded by communication complexity with the promise version of the universal relation plus an extra log m bits. Okay, so how do we prove that? The proof is fairly straightforward. So let's say we have a protocol that solves the promise version. Okay, so pi is a protocol that solves um, or indeed it is. So if you give pi inputs x comma y, so Alice gets x and Bob gets y, it produces an index I in M such that xi not equal to yi, but it's only guaranteed to produce such an index if x is not equal to y. Okay, so pi is a protocol solving this one. So we want to use this protocol to come up with a protocol for the non-promise version of the universal relation. Okay, so how do we do that? Here's the thing, like we are in the setup where Alice is given x, Bob is given y. They don't know if x is equal to y or x is not equal to y. But if x is different from y, they are supposed to find an index like above. And if x is equal to y, they can say reject. So what are they going to do? So they can just run pi on xy. So by the guarantees of this promise version of universal relation, if x was indeed different from y, so if x is not equal to y, so this would indeed output an index where xi is different from yi. But when x is equal to y, we don't know how it behaves. It might behave in a completely erratic manner and output some random index. So if x is equal to y, there's no index where x and y are different, right? But in the non-promise version, we need to distinguish these two cases. So we run pi, we get this index. We don't know if it is a valid answer or not. But this is a relation where we can check if the answer returned by the protocol is a valid answer or not, right? So what do they do? So maybe at the end of the protocol, only maybe Bob knows the answer or only Alice knows the answer. So we can consider like models where not necessarily both the players know the answer, but at least one of them knows the answer. So let's say at the end of the protocol, so Bob knows I. So what can he do? He can send this index, which is allegedly the separation between x and y that is returned by pi, to Alice. So I'll send I to Alice. Right? So now Alice can also send yi. So his input bit on that index. So he sends these two information. This is not costly. So this is where the log m comes from. So maybe I need a log m plus 1. So to encode I, this is a value in 1 to m, I just need log m bits. And to encode this yi, I just need 1 bit. So this is 1 bit costly and this is log m bit costly. So maybe this is like plus 2. So I'll need something more. So now what do they do? So now Alice knows I and she knows yi. She can just check internally if xi is different from yi. If xi is indeed equal to yi, then we know that the only, okay, so this is what Alice does. Alice checks if xi equals yi. In the yes case, she says output but or reject. Okay. And in the no case, that is xi is xi is different from yi, she outputs I. Yeah, or they agree that I is the difference. Okay, so why is this protocol correct? So we can claim, so to prove the correctness, we need to argue that correctness, this modified protocol outputs perp if and only if x is equal to y, right? And this is fairly straightforward. So if x is not equal to y, we can show that it never will output perp. If x is not equal to y, then pi is guaranteed, because then the promise of the universal relation is satisfied. Then pi is guaranteed to give you an index where xi is different from y, right? So if x is not equal to y, the index that is produced by pi is a witness, is a valid witness. So Alice would never reject. So this case would never happen. The yes case would never happen. So if x is and if x is equal to y, no matter what I the protocol returns, it is going to be all the same. Yeah. So this shows that, so given a protocol for the promise version of universal relation, we can come up with a protocol for non-promise version of the universal relation. So the best protocol for the non-promise version of the universal relation cannot do worse. Its complexity cannot be larger than this, right? So here is a protocol that solves your problem, let's say with like this many bits. So the best protocol in fact only can minimize or decrease the number of bits. So this shows that the communication complexity of the non-promise version is comparable to the communication complexity of the promise version modulo some log m bits. So if you're ready to like forgo this plus or minus log m, it's fine. Yeah. Are there any questions about this proof? Okay. If not, let me move on. So our revised goal is to okay. So we need to prove. So to prove a lower bound on the communication complexity of the universal relation on m bits, it's enough to prove lower bound on communication complexity of the universal relation where there's no promise. So this dash means why is that? Because of the upper bound that we proved. So any lower bound here would be a lower bound for, so let me do this in. So any lower bound that you prove here would be a lower bound for this one by this inequality minus this log m plus 2. So if you don't mind about this additive loss, this is well and good. Okay. And the non-promise version, as I was telling you earlier, looks very close to equality problem, right? Because, so what was the um dash problem? So Alice is given x and Bob is given y. If x is different from y, output index such that xi is not equal to yi, and if x is equal to y, output reject. So this one seems more like equality. So before they can decide on the output of the protocol, they need to really know if x is different from y or if x is the same as y. And this seems like they need to solve at least the equality function on their inputs. Okay. So, and we kind of saw one proof of why equality is difficult, but I'll show you a simpler proof based on the rectangle property that we saw from last lecture. So what did and I want to build on like the intuition from this proof to prove a lower bound for the non-promise version of universal relation. Okay, so here is a quick detour into equality. So equality on m bits. Alice gets x, Bob gets y. Goal is to output 1 if x equals y, 0 otherwise. Okay, and we said we had this rectangle property which said that for any deterministic protocol we have, so if you look at the node of a protocol, so it's we have some deterministic protocol pi. So if you look at a node, we can label it with a rectangle x cross y. So x is set of inputs of Alice and y is set of inputs of Bob. And let's call this node pi. And what was the how was x and y defined? So a specific input x comma y is in this rectangle x cross y. If you run pi on x comma y, it reaches this node small pi. So basically it's a deterministic protocol, so on any input, on any given input, you only follow one specific route to leaf path, and the rectangle associated with a specific node is all the inputs that would reach them. And it was, so in the last lecture we saw that it is indeed a rectangle. So if xy is in, so as in like it's a cross product of some inputs of Alice and some inputs of Bob. Okay, so and this property implied that, so if we have two inputs, let's say xy, which is in x cross y, and x dash y dash, which is in x cross y, because it's like a cross product of two distinct sets, we also get so this is xy, this is x dash y dash. We also get that xy dash is in the set, implies that xy dash in the same set, right? And we also got this extra point, which was x dash 1. Oops, sorry. Okay, so now we can use like a very simple proof to show that communication complexity of equality on m bits is at least m minus some constant, m minus 1. I think m minus 1 would work. So how do we do that? So remember this communication matrix that we introduced in the last lecture. So you consider all possible inputs of Alice and all possible inputs of Bob. So here you had all x's which were in 0, 1 to the m, and here you had all y's which were in 0, 1 to the m. So this is a 2 to the m by 2 to the m matrix. And what are the diagonal entries? So these are all, so these are the equal values. So the equalities, if you, so this is 0 to the m, and this is the string 0 to the m. So this is 1 to the m, and this is also 1 to the m. So these two strings are equal. The value of equality here is 1, and similarly the value of equality here is 1. In fact, we saw that equality is 1 on all the diagonal entries, and it's 0 elsewhere, right? Because nothing else is equal. So this is in fact the identity matrix. And now I claim that, okay, so suppose so how are we going to prove that the communication complexity of equality is at least m minus, at least more than m minus 1? We'll say that, say you have a protocol that solves equality with less number of bits, we'll come up with a contradiction. So this was kind of an adversarial argument. So suppose the excess pi such that communication complexity of pi is strictly less than m minus 1 and pi solves equality on m bits, then we want to imply that there is a contradiction, or pi. We want to say that this protocol ends. We want to. Okay, so how do we do that? So first, I want to claim that so the pi is some protocol tree like this, right? And at the leaf of the protocol tree, it has to, because it is computing the equality function, it has to say either equality is 1 or equality is 0, right? And given any possible input to Alice and Bob, it would only end up in one of the leaves, right? So maybe I'll try running the protocol pi on 0 to the n, 0 to the n. Equality's answer should be 1. So this input should finally reach a node, leaf node, where it is 1. Okay, right? So this kind of a pigeonhole kind of argument. Every input should reach one of the leaves. And how many leaves are there? So this communication protocol complexity of pi is at most m minus 1. So the height of this tree is less than m minus 1. So how many leaves can it have? It's a binary tree. So the number of leaves, of pi is strictly less than 2 to the m minus 1. Or, yeah, because the height is at most m minus 1. We can even work with less than equal to. Okay, so what's the problem with that? So now let's go back to the matrix and select the one inputs of equality. So these are all strings which are equal, right? These are all x comma x pairs where they are equal. So how many of them are there? So number of x comma x pairs is exactly 2 to the m. So x is an m-bit string. Once you choose x, what you give to Bob is the exact same string. So there are only 2 to the m choices. Now we are going to claim that so given x comma x dash, which is like both m-bit strings, but x is different from x dash, I claim that xx and xx dash cannot go into the same leaf. Same leaf of pi. Why? Because in the leaf, so even in the leaf, so there will be like some, so in the leaf there will be some value, either it's 0 or 1, and even the leaf has an associated rectangle. So we are considering the case where the associated with rectangle with the leaf has both xx and x dash x dash. Sorry, this should be x dash x dash. So this contains xx and x dash x dash. So what happens when you have this? By rectangle property, you get additional inputs. What are the additional inputs? So let's consider what is the situation here. So the situation is that we are in a rectangle where Alice has x and x dash, and Bob has, so this point is in the rectangle, xx is in the rectangle, x dash is in the rectangle. What additional points do we get? We also get x dash x, and we also get xx dash. Now I claim that there is no value that the leaf can answer, so that the answer is correct on the entire rectangle. That's straightforward, right? I mean, if it says 1, that means the strings are equal. All the strings in this rectangle are equal. But since x is different from x dash, then this answer being 1, here it is, it's wrong and it's an error, right? So in the case if it is 1, this leads to an error on this pair of inputs. And if it is 0, it leads to an error on these two pairs of inputs. So if you give x and x, it should be 0, it should be 1, and the protocol is saying 0. Because it's a deterministic protocol, it has to like choose an answer. It can't say 0 or 1 based on input. And because all these 4 inputs are there, there's no one answer that it can say. Yeah. So maybe the thing that makes equality hard is that these inputs where the players like have all the bits equal, so they have to separate this diagonal from the rest of the matrix. So this is the hard part. So they have to figure out whether x is equal to y or x is not equal to y, and like they have to separate them, these inputs, into different bins, otherwise there will be a problem. So this diagonal has to go into different leaves. So how many leaves should there be? There should be at least as many leaves as there are x comma x pairs. So the number of leaves should be at least 2 to the m. But we know that number of leaves of pi is at most 2 to the m minus 1. So there will be one leaf which has at least 2 of these pairs, and then we are done. On that leaf, the protocol would make an error. So this shows that communication complexity of equality is at least m. It cannot be m minus 1. Yeah. Okay. So we're going to try. We're going to prove something similar for universal, the non-promise version of the universal relation. Okay. And we will remember that the hardest inputs for equality was the strings where they were exactly equal. And we're going to use these inputs to come up with a set of hard inputs for the non-promise version of the universal relation. So goal, lower bound for dash. Okay. So what we want to do, we'll try for a similar thing, but here I'll try to prove that this is at least m minus 1. Okay, or So how we're going to do this? We are going to again do a adversarial argument. Okay. So let's suppose that this is not true. Suppose there exists a deterministic protocol pi that solves um, dash in less than m minus, so less than m, strictly less than m minus 1 bits. So that means less than m minus 1 bits. So this implies that the communication complexity of this particular protocol is at most m minus 2. So then we want to show that, then show that pi errors. Okay, so this is what we want to do, and we want to use this inputs which are equal for both Alice and Bob as sort of a hard distribution for this protocol pi, and we'll make sure that on using these inputs we can show that such a super efficient protocol must make an error. Okay, so how do we go about this? We sort of saw this argument like very quickly at the end of last lectures, but I'm just gonna recap it. So the idea is going to be, the philosophy is going to be this, can be summarized in one line: keep the symmetry as long as possible. As long as possible. Okay, this might sound very cryptic to you, but what do I mean by that? So if you think about a protocol pi, what happens is that in the root of the protocol, Alice and Bob has no clue what their inputs are like, what each other's inputs are like, so they've made no progress. But what happens? So this is like basically 0 1 to the m cross 0 1 to the m. Bob could be getting any string, Alice could be getting any string. So remember that this is the case for the root of the non-promise version. In the promise version, it's not exactly even a rectangle, right? If Alice gets an x, Bob should not get that x as the input. But since we are in the non-promise version, there's no guarantee that x is different from y. Alice could get any m-bit string, Bob could get any string, any m-bit string. So what they're doing is like they do communication. So maybe here it's Alice who speaks. Alice divides her inputs. Let's call this x, let's call this y, into two parts, x0 and x1. So like Bob knows, Bob can narrow his search for what Alice's input is into one of these partitions. So as the protocol progresses, they restrict the set of possible inputs further and further until they get to a point where they know that in the associated rectangle there is only one answer. Okay, yeah. So but in the universal, in the non-promise version of universal relation, what is the answer? Like the answer is either an index where x is different from y, or it is perp, in which case x is equal to y, right? If it is perp, then there can be only like one set of it. So here is the thing. So if the label of the leaf is perp, then in the associated rectangle x cross y can only have some x comma x. It can only contain like one set of inputs x comma x, because if you have, the moment you have some other y, so if it also has some if not, there exists some y comma y also in x cross y, right? And the moment you have x comma x and y comma y, x and y are different strings, you also have by the rectangle property, you also have x comma y and y comma x. But on x comma y, perp is not a valid answer, right? They can output perp only if they know that the strings are equal. So from by looking at the leaves where they have to output, where they can output perp, they have to like narrow it down to just one single input. So this is very hard. So they have to like make sure that there's only like, if they are outputting perp, they have to make sure that there's only one input in the rectangle associated with the thing. And we'll also see that in the rectangle associated with an answer where they say it's some I, there cannot be too many inputs either. Okay, but before even getting to that, they have to figure out if they're in the perp case or they're in the I case. So here, so to delay their progress on finding an I as much as possible, we're going to keep a set of inputs where there's always like some input in that, like some large fraction of inputs in that set where the protocol has to output perp. Okay, and so here is the idea. So so initially, so we will keep track of a set of inputs S such that for all x and s, xx can be, so this set of inputs is going to be associated with a node in the protocol. So we'll start with the root and we'll go all the way down to the leaf. Update this set as we move from one node to its children. So yeah, it's a good idea to like denote it with subscript pi, set of inputs s pi associated with a node pi, such that for all x and x comma x belongs to the rectangle of pi, is in x pi cross y pi. So we'll just use this notation to denote that x pi is the Alice is part of inputs associated with the node pi, y pi is the Bob part of inputs associated with the node pi. Okay, so these are like the inputs. So this is the symmetry part of this problem. So these are the inputs which can be given to both Alice and Bob, and until they have ruled out all such inputs, they cannot come up with an answer I. So we want to keep these. So what is our goal? We are given this protocol pi, which has many paths, right? So this is the root of the protocol. So we want to trace a path in this protocol. So we'll start from the root, we'll go to one of its children, then one of its children, one of its children, all the way to the leaf. So that the S pi that we are looking at any time is quite large. So this is the symmetry part, and we want to keep this symmetry part large as long as possible. Okay. So how can we do that? So how can we do that? So here is like here is what happens. So initially at the root, what is S root? So you can, because Alice and Bob can be given any string x comma y, the S root is the set 0 1 to the m. It's the entire set of inputs that can be given to both Alice and Bob. So now at the root, maybe Alice speaks. Without loss of generality, let's assume that Alice speaks. So what happens? So here is x cross y of the root. So nothing happens to the y part because Alice is speaking. She's going to restrict her inputs based on her message. If it's 0, she knows, she's telling Bob that, okay, look, my input comes from this part of xr, and if it's 1, it's coming from the other part of xr. So what happens is that Alice gets like 2 children, and the rectangles associated here would be, let's call this x0 cross yr, and this would be x1 cross yr. And the guarantee is that xr is a disjoint union of x0 with x0 union x1. Okay, but what happens to S pi at these 2 different nodes? So let me call this pi 1 and pi 2. So what is S pi 1? So S pi 1 is everything of S root. So all the strings that were in S root can still be given to Bob, right? everything, because the y of the root is the same as y of pi 1. Yeah, so there's no change in terms of what inputs you can give to Bob, but there's a change in terms of what inputs you can give to Alice. So Alice restricts her set of inputs to x naught. So s pi 1 has to be restricted this way. So s pi 1 shrinks like this, right? And what happens to s pi 2? It's just basically s root, but you can only give strings from x1 for Alice, and since we are looking at s root as s pi as a set of inputs, where Alice and Bob gets the same input, they can only be given something from x1. Yeah, so this shrinks like this. So now we can claim that s pi 1 and s pi 2 form a partition of s root, right? So then there should be like s root. So one of them should be at least half s root. So either there exists b in 1, 2, such that s pi b is at least s root by 2. So we can, if it's Alice speaking and it's like this, we can descend onto one of these nodes and keep the set of inputs which can be given to both the players to be at least half the size in the root. So initially we had all the symmetry, but a bit of communication of Alice could break this symmetry very badly. But on at least one of these sides, it breaks the symmetry only by a half, right? So if you take symmetry to be the number of inputs that can be given to both the players, so on at least one path, this symmetry only breaks by half. This cardinality only breaks by half. And what happens to when Bob speaks? So if you're at a node, let's call it pi, and this is a node. Okay, so let's call it pi outside. And this is a node where Bob speaks, and this what happens to this rectangle x pi y pi. This is pi 1, this is pi 2. So the x pi doesn't change. So because it's Bob speaking, nothing happens to the Alice side of the inputs. So this is still x pi 1, but this becomes y0, and this is 0, this 1, this is x pi 2 cross y1. So now and we are by induction we are keeping track of this inputs s pi. So these are set of strings in 0, 1 to the m which can be given to both Alice and Bob. So now by doing this, the set of inputs that can be given to Alice hasn't changed at all, but some of the inputs cannot be given to Bob, so we need to update s pi 1 and s pi 2 accordingly. So s pi 1 would be what? It would be s pi intersection y naught, and s pi 2 would be s pi intersection y1. So now if we update s pi in this manner, you can see that for all x and s pi, so maybe not call it x because these are like, I don't know, these are like template inputs that can be given to both the players. Let's call it z. So for all z in s pi, z belongs to this rectangle x pi cross y pi. Yeah. If we do our updates this way, this invariant is maintained. For any node that we go to, and there's another invariant that we maintain. So how do we find a path? So among these two things, we will go down the path where, so we will go here if and only if s pi 1 is larger than s pi 2, and if s pi 1 is at least as large as s pi 2, this implies that s pi 1 is at least s pi by 2, right? Yeah. So this is invariant number 2, but So the first invariant was true for any node in the protocol. The second invariant is true for the nodes in the path that we are constructing one by one. So the invariant is that on the path that we trace, so if we go through pi and then we go to one of its children pi 1, it is the case that s pi 1 is at least s pi by 2. So what happens, so if we maintain these two invariant, what happens after m minus 2 steps? So we started with root, then we found one of its children, left or right, then we found one of that node's children, go on, so on and so forth. After m minus, so maybe I said m minus 2, after m minus 2 steps, because the protocol had depth communication complexity m minus 2, after m minus 2 steps, we would have traced our path to a leaf. After m minus 2 steps, we are at a leaf, right? And what happens here? So what is, let's call this leaf by the L. So what is cardinality of SL? So here we had, what is cardinality of S root? This was all, so what are the strings that can be given to both Alice and Bob at the beginning of the protocol? Because it's a non-promise question, it's any string on M bits. So this was 2 to the M, and when we come here it becomes 2 to the M by 2, when we come here it becomes 2 to the M by 4. So after M minus 2 steps, SL should be at least 2 to the M minus 2, 2 to the M divided by 2 to the M minus 2. This is because we always choose the heaviest side. So this is at least what? 2 to the 2, which is 4. So there's at least 4 inputs that can be given to both the players. So I just need 3 inputs to complete the argument, but because we have to deal with the power of 2 in this argument, I'm going to, I'm assuming that the length of the protocol is m minus 2. So let's say, so we are at this leaf, and we know that SL is at least 4. So let's say SL contains 3 distinct strings, Z1, Z2, Z3. This assumption is weaker than what we proved. There should be another C4, but to prove that the protocol makes an error, this is enough. Okay, so SL contains Z1, Z2, Z3. What happens? So what could be the label of it? L is a leaf, right? So what could be the label of L? So in the beginning we saw that the label of L cannot be perp. The label of L cannot be perp because, okay, on Z1 it can say perp, but Z2 is also there. On Z2 it can say perp, but it cannot say perp on Z1 Z2. So if it says perp, this is an error. Yeah, this is crucial. This is clear. So label of this L cannot be perp because we not, the only way it can have perp as a valid label if it says only one thing in this SL, but there are like at least 3 things. So now it's the other condition. So what if label of L, that this leaf, is some index I in M? So what does that mean? So that means that for any possible inputs, so for any pair of inputs xy that reach this leaf, it should be the case that xi is guaranteed to be different from yi. And I claim that this cannot happen. So what do we have? We know that, so what are the inputs that reach this, that reach this leaf? So we know that SL was Z1, SL contained Z1, SL contained 3 distinct m-bit strings Z1, Z2, Z3. Okay. So what was the definition of SL? This is all inputs such that these inputs can be given to both Alice and Bob. So let's denote x cross y be the rectangle associated with L. With L, then we know that z1 z1 is an x cross y. Why is that? By definition, we are only keeping those strings in SL which can be given to both Alice and Bob. So z1 is an x cross y. Similarly, z2 is an x cross y. z3 is an x cross y. But by rectangle property, we get a lot more inputs. So let's denote this by a picture. So the condition that we are in, these are the set of inputs of Alice, and these are the set of inputs of Bob that reach this node, this leaf. Okay. And because by rectangle property, we get that all these pairs of inputs. So where you choose one thing from here and another thing from here are in the rectangle of L. Okay. So now we claim that the answer for that in this leaf. So the assumption was that this label of L was some index I. Okay. So what do we do? So we want to say that this label is a wrong answer. So we should produce a pair of strings. So how are we going to prove that this is wrong? This is an error. So we will produce a set of inputs x comma y such that xi is equal to yi, and a set of inputs x dash y dash such that x dash I is different from y dash I. And the condition is that both of them belong to this rectangle. So they belong to rectangle of L. So in this case, we know that I is not a valid answer, because when I is a valid answer if and only for any pair of inputs, xi should be different from yi, right? So the first pair is easy to get. What do? You just consider z1. Now we need to we need to guarantee that there is also a pair where no matter what this I is, it's going to be different. Yeah. So how do we do this? So we are given three strings, right? We have z1, z2, z3, and we are claiming that we want to say that so no matter what the I is, so claim for any I in M, there exists a pair zi zj such that, okay, let's not call it zi zj because I used I already. So let's say, so there's a pair from here. So I don't know, there's a pair za zb such that za at I is different from zb at I. Okay. So how do we prove that? So let's look at so the protocol is saying that they differ at some index I. Let's write that index I down, and in the corresponding entry for z1 we will write what is z1 of I. So z1 of I is a bit, it's either 0 or 1. Let's write it as 0. Okay, let's say z2 of I is 1, or z1 of z3 of I. Yeah. Oh no, so I want to prove that, okay, so what I want to prove is slightly different from this. So but so I want to say that, so we are in the case that the protocol says it output I, right? So we want to say that this is a wrong answer. So if it is indeed a correct answer, there should be a z1 So there should be a pair CA-ZB such that ZA of I is different from ZB of I. So in that case, I want to also show that there is a pair where that's not the case. Yeah. So how do we do that? So because this I has to be a valid answer, so there should be like at least, so we are actually done. So there should be at least one pair where they differ, right? So because I is a valid answer, there should be some thing. So if the label of this rectangle is indeed I, so this means that there is some inputs where this I is a valid answer. So that means that Z1 of I should be different from Z2 of I. But we know that there cannot be, now we have to show this part. So this part is guaranteed because we are assuming that label of I is a correct answer. So if label of L being I is not already wrong, it must mean that there are two inputs where these inputs differ on I. So yeah, so there's, let's say it is Z1 and Z2. So we get an input where these two things are different. But now we need to show that these two, like there is also a pair of inputs where Xi is equal to Yi. How do we do that? It's fairly straightforward. We can just pick the inputs to be Z1, C1. No matter what your I is, they're going to be the same, right? There's no I which can show the separation between Z1 and C1, and there's no I which can, there's no I that can show that, like that can witness the difference between Z1 and Z1. So because we kept this symmetry until the very end, there is a pair of inputs. So particular, this would be Z1, Z1, where it has to output perp, and if it is like it is outputting I, there must be some other pair of inputs which is where it is witnessing that difference, or it's already wrong, right? So just to simplify what I'm saying, claim that so on this rectangle Z1, Z2, Z3, you cannot output I, just for the fact that say you output I. So then on all these things you have to say I is a witness, right? So I is an index where these inputs differ. But this is definitely wrong. Why? Because on Z1, Z1, is there any I that you can find where these things are different? No. So this leads to error as well. So if you output I, there's an error because you can take Z1, Z1. And similarly, if the only other options, because it's a leaf, they have to say either I or they have to say perp. And we saw in the beginning itself that they cannot say perp. Why is that a problem? If they say perp, they have to say perp on all of these inputs. And clearly on this input, you cannot output perp because Z1 is different from Z2. On pi on Z1, Z2 cannot output perp. Okay, so this is the argument. So the moment you have actually, so I don't need three inputs, I just need two inputs. So the moment you have two inputs, two strings Z1 and Z2 which can be given to both the players, there's no one answer that you can give. You cannot say I for any I in M, nor can you say perp, because if you say I, you will be making error on the diagonal, and if you say perp, you'll be making an error off the diagonal. So this is like the argument for equality, right? But yeah. So what does it show? It shows that any protocol that solves a promise version should speak M-2 bits. Okay. And what is the lower bound that we get? So this shows that the communication complexity of the promise version of the universal relation is at least M-2. And what do we get? We saw this fact earlier that the non-promise version plus some log m is an upper bound on the promise version. Some constant, something like 2. So what do we get? What's the final lower bound that we get for the promise version? So this is the promise version. It's that so we know that this is at least m minus 2. So this is m minus 2 plus, so minus log m minus 2. So this is something like m minus log m minus 1. But remember that in the beginning of the lecture that I did say that we'll show that communication complexity of the universal relation on m bits is at least m minus 2. So how do we do that? So that is a bit more involved. It's the same argument. It's just that so note that we here, to prove that the protocol is erroneous, we use two kinds of inputs. An input, so in one case we had to use an input where they were both equal. Alice and Bob had the same string, right? So this is not a valid input for the non-promise version of the protocol. Yeah, so I'm just saying that in this case we had two cases. So we had two cases based on label of L. So this is either I, some index I, or per. So in case it is per, it's simple. So one of the off diagonal entries is wrong, and if it is I, we say that Z1 C1 witnesses an error. On Z1 C1 there is no I that can be different, right? But Z1 Z1, so giving Z1 Z1 as an input to Alice and Bob is not allowed in the non-promise version. So this not really this argument would not work for the non-promise version, but a modification would work. So we'll see that, and yeah, that's we'll see this next. So remember that, okay, so the non-promise version was very easy. So once we had this philosophy that we want to keep the symmetry as long as possible, we maintain this. So for every node L, we maintain this set of inputs SL, which can be given to both the players. And at the end, we could easily prove that if the communication was less than m minus 2 bits, the protocol made an error, right? In the non-promise version, in the promise version, you have to do more work. Okay, so why is that? So, and the lower bound based on the non-promise version was good, but it had this loss factor. So we would ideally want to get rid of that. Yeah. So how do we do that? So there is this tricky part. So now, how did we define S of a node? So we defined S pi to be the set of strings C from 0, 1 to the m, such that, so this is a node pi, and we have a rectangle associated with pi. Those are the set of inputs that reach that node, such that this Z was an S pi if and only if this input ZZ belong to this rectangle. But in the promise version, we don't have any. This is not even a legal input, right? So remember the promise version of universal relation, Alice has to be given an input X such that the Bob's input Y is different from X. So the protocol, we are not guaranteed anything about the behavior of the protocol on these kind of inputs. Okay, so our definition of S pi has to be slightly modified. Yeah. So we would say that so these are a set of inputs that can be so so ZZ is not even a valid input. So we can try to modify our definition to work with the promise version as follows. So S pi for the promise version, it's again going to be the set of all strings Z. It's a subset of, again, it's going to be a subset of strings of length M. So they sort of have symmetry. But the guarantee is that if you have uh, Z1 in S pi and Z2 in S pi, and if C1 is different from Z2, then we are guaranteed that Z1, Z2 is in X pi cross Y pi. So what does it mean? So S pi is just a collection of strings. So earlier these were the strings that, like, from these strings we formed an input by giving the string to both Alice and Bob. So now the way we are forming an input is like we first pick one string from S pi, let's call that Z1, and one we'll take another string which is different from this string, let's call that Z2. So that is from S pi minus Z1, and give that to Bob. So earlier this was our picture, so we had S pi, we will pick a string Z and give it to Alice and Bob and analyze the protocol's behavior on that, right? But in the promise, in the promise version, the protocol doesn't have to be correct on these kind of inputs. So we can't analyze the protocol on these kind of inputs. So what do we do? So what we're going to do is like we're going to maintain S pi in a way that the following process always works out. So we will first sample Z1 and give that to Alice. Alice gets Z1. So from everything else that is not Z1, we will draw Z2 and give it to Bob. So no matter what Z1 and Z2 are, Z1, Z2 should be a valid input in the corresponding rectangle. Yeah. So what is S root? So with this modification, what is S root? So initially in the any protocol solving the promise version or the non-promise version, like initially they don't know anything about their inputs, right? So what is S root? I claim that S root is it's still 0, 1 to the M. Why is it so? So if I pick any Z1 from it's any binary string, and then I pick a Z2 such that Z2 is not equal to Z1, then I can give Z1 to Alice and Z2 to Bob, and all the promises of the universal relation are kept, right? So by this modified definition of S pi, where like this is the modified definition, so if you choose two different things from S pi, you can give one of them to Alice and the other to Bob. With this modified definition, S root is still 0, 1 to the M. It's still set of all strings. And now you can see that like the earlier argument of S pi halving at each point, that also works. Yeah. But what happens at the end? So this is something you can check for yourself. Invariant 1 and 2 hold. So invariant number 2 holds that if you're at a node pi and it has, let's say, two nodes pi 0 and pi 1 as children, there exists b in 0, 1 such that either this S pi of b is at least S pi by 2. This set S pi at least, so at most shrinks by half each time we go down in the protocol. So this you can check for yourself. This invariant is like maintained, and invariant number 1 is the definition of S pi. So that is also maintained. That's something that you can check easily. So what happens? So after m minus 2 bits of communication, so here you're at S root, that is cardinality of S root is 2 to the M. Again, after m minus 2 steps or m minus 2 bits of communication, we would reach a leaf L. Yeah. And what are we guaranteed? Again, we are guaranteed that SL is at least S root by 2 to the M minus 2. So this is at least 2 to the M by 2 to the M minus 2, which is like 4. Yeah. So now we want to say that the protocol errors. We want to like use the same argument that we used in the, okay, not the same argument, but a similar argument that we used in the non-promise version to come up with set of inputs where the protocol makes an error. So what are the possible labels of this leaf? Can they output perp? No. Perp is ruled out because we are in the promise version. So they need to produce some kind of valid output only if the inputs are guaranteed to be different. So we cannot analyze the protocol on the diagonal. So that was sort of our main thing when we did the non-promise version, right? We analyzed the diagonal entries and the off-diagonal entries. So in one case, the diagonal entry was wrong, and in the other case, the off-diagonal entry was wrong. But in this in this particular setup, you cannot use the diagonal entries. So what do we do? Again, we know that SL contains three elements. SL contains Z1, Z2, Z3. But earlier, so what does that mean? So pictorially, what does that mean? So we have Z1, Z2, Z3. So any of this can be given to Alice. So Alice can get any of this. But then Bob should get a string which is not the string that is given to Alice. So we cannot analyze the protocol on certain inputs. So what inputs of, so I'm going to mark out the inputs which are not even valid. So what are they going to be? So they're going to be the diagonal entries. But by the definition of SL, Z2, Z1 is a valid pair of inputs that the protocol has to output correctly, and Z3, C2 is another, C1, C2 is another, Z3, Z1 is another, so on and so forth. And what can be the answer? We saw that perp is not an answer because we are in the promise version. So the answer, so the label of L should be some I in M. So all these things should be labeled as I. And I want to say that this is impossible. So what should be the property? Like if it's labeled I, Z2 should be different from Z1 at I, C2 should be different from Z3 at I, so on and so forth. On this 1, 2, 3, 4, 5, 6 valid pairs, I should witness a difference. And I claim that that's not possible. Why is that? Can anyone guess? So this was the argument that I was trying to do. So I sort of did the promise version argument in the non-promise part, but let's do it now. So we have three strings Z1, Z2, and Z3, and let's mark their ith value. So because they are binary strings, let's say Z1 is 1, Z1 is 0, Z2 is 0, Z3 is 1. So in this case, we know that Z1, Z2 on Z1, C2, pi on Z1, C2 cannot say I. Why? Because Z1 of I is equal to Z2 of I. Right? So in this example, I is not a valid answer. But this is one of the many possibilities. The other possibilities maybe this is like 1, 1, 0. But in this case also, there is like two strings which are equal. Okay, in this case, it's also Z1, Z2. But maybe it's like 1, 0, 1. Again, you have a set of inputs where I does not witness a difference. And these are all off diagonal entries, right? The Z1, Z2 are strings, are valid inputs to the promise problem. We know that SL contains three unique strings, Z1, Z2, C3, so no two of them are the same. So any pair of them is a valid input to the promise version. And I claim that no matter what you say, there will be at least a pair where this either Z1 of I is equal to Z2 of I, or Z3 of I equal to Z2 of I, or Z1 of I equal to Z3 of I. So there at least one of these three pairs should be equal on I. Can someone think of why that should be the case? So we saw three examples, and we saw that okay, on these three examples, indeed there is a pair where the value on I is equal, but you can generalize this intuition from this example to say that indeed no matter what 0, 1 values you plug in, there should be two things which are equal. Okay, maybe I lost everyone at this point, or it is too easy. I don't know. Anyone has an idea? Okay, if not, it's pretty straightforward. So what is the thing? So you have three possible. You have three locations, right? You have Z1 of I, Z2 of I, and Z3 of I. But they're all binary values. There are only two possible values in them. So this is kind of a pigeonhole argument. So the pigeons are Z1 of I, Z2 of I, and Z3 of I. And the holes are the value that they hold. And because these are all binary strings, all these three values has to be either 0 or 1. So there are three pigeons and two holes. So there should be at least one hole with two pigeons, right? So what does that mean? So there's either so maybe these two go into here, or maybe this and this goes into here. But in any case, there's one pair among Z1, Z2, Z1, Z3, or Z2, Z3, which ends up having the same value at I. So no matter what I is, there will be like at least one of these pairs which will have the same value at I. So I is indeed not a valid answer on that pair of inputs, hence the protocol is wrong. So this completes the proof that the communication complexity of the promise version of the universal relation is also m minus 2. Okay. So if we are slightly lost in the details, the main takeaway is this philosophy that we want to keep the symmetry as long as possible and then break the symmetry only at the very end. So we are kind of in the promise version, the non-promise version, you could like give the same set of inputs to both the players. You could this definition of this symmetric inputs were much cleaner, but even in the promise version, it's not too bad. You have and you want to make sure that this set of symmetric inputs that you keep only shrinks by certain amount every time you communicate. So if you don't communicate too much, the set of symmetric inputs is still large, and if you have symmetry, Alice and Bob cannot really know if x is different from y or if x is equal to y. Yeah. So yeah, that's all for today. I'll stick around if you have any questions, and in tomorrow's lecture we'll see the first serious lower bound in this whole course, and that will be on lower bound for composition of universal relation.